Okay, let's talk about ellipses and hyperbolas, 5.2. Okay, so an ellipse is the set of points in a plane whose distances from two fixed points in the plane have a constant sum. The fixed points are called foci, right? That's the plural of focus. So one of these things is called a focus. Two or more of them are called foci. Okay, so note that ellipses are closely related to circles, right? A circle is just the set of points whose distance from one fixed point is constant. An ellipse is the set of points whose distance from two fixed points is constant, right? Loosely speaking, right? The sum of those distances is constant. That relationship is even more clear when we look at the equation for an ellipse, which we'll do in a second. But what I want you to do for now is pause the video, follow this link to watch somebody drawing an ellipse based on the definition that's given here. Okay, I'll post this video in Canvas, right, in the Canvas module for 5.2, so that you can take a look at it there. But go ahead and pause the video and watch this video right now. Okay, so now that you've done that, hopefully, here's the equation for an ellipse, right? So the equation of an ellipse with foci at negative c0 and positive c0 is given by x squared over a squared plus y squared over b squared equals 1, where 2 times a is the fixed sum of the distances between a point on the ellipse and the foci. Another word for that is we call that the major axis. So a is the major axis. And b squared is a squared minus c squared, right? So we call b the minor axis, but yeah, b squared is a squared minus c squared. When it comes to actually graphing ellipses, I'm usually not thinking of a and b in quite this way, all right? And I'll talk about how I think about a and b when we come to actually graph them. But for now, this is the equation for an ellipse, and let's prove it. So let's say that xy is a point on the ellipse. The distance between focus 1 and xy, remember focus 1 is negative c0, so that distance, I'll call it d1, I guess, is the square root of negative c, well, maybe I'll do it the other way around, x minus negative c squared plus y minus 0 squared. In other words, it's the square root of x plus c squared plus y squared. The distance between f2 and xy, I'll call that d2. This is the square root of x minus c squared plus y minus 0 squared. Okay, so in other words, the square root of x minus c squared plus y squared. Okay, now by definition of an ellipse, the sum of these distances, d1 plus d2, is 2a, right? It's 2 times a. So since that's the case, we know that square root of x plus c squared plus y squared plus square root of x minus c squared plus y squared, we know that that sum equals 2 times a. And if that's the case, then we can move this term over to the other side. Then we can square both sides and we get something really nasty, right? Then we can isolate this radical again and square both sides again. And then we can do some regroupings. Remember that a squared minus c squared is the same thing as b squared. And then divide through by a squared b squared, and we get the desired result. So I'm not going to take you through this line by line, right? But you should be able to read through it and kind of follow along what's happening, right? We're squaring both sides, isolating the radical, squaring both sides again, simplifying, regrouping, right? And then dividing through by a squared plus b, or a squared times b squared. Okay. Now, this is the case notice that the foci, here we're on the x-axis, right? Negative c0, positive c0. But if the foci were on the y-axis instead, then we would get, if the foci were on the y-axis instead, we would get this equation, x squared over b squared plus y squared over a squared equals 1, where a is still your major axis, right? So 2a is still the distance between the foci and the points on the ellipse. And then b squared is still a squared minus c squared. I'm going to leave this to you as an exercise, right? So it'll be an exercise for you to prove that that is in fact the case. Okay. But for now, I want to talk a little bit about graphing these things. Okay. So another thing to note is that in the derivation we did earlier, since the foci were at negative c0 and positive c0, the center of the ellipse is at 0, 0, right? Right in between the foci. So more generally speaking, let's say that the ellipse is centered at some point hk. Then the equation for the ellipse would look like this. It would look like x minus h squared over m squared plus y minus k squared over n squared equals 1. And I'm using m and n instead of a and b because a and b meant something very specific on the previous page. And I want to think of these numbers a little bit differently when I come to graph them. Okay, because when I go to graph this, here's how I'm really thinking about it. I'm thinking, okay, this ellipse has center hk, and then it has vertices. In other words, the points on the ellipse are going to be m units left and right of center, and n units above and below center. Okay, that's not always true if you're dealing with a and b, right? So I change the letters to m and n so that we can make this more kind of general observation. Okay. Just like with parabolas and circles, h is always with the x's, k is always with the y's, and you always change the signs. M is always what you're dividing the x group by, n is always what you're dividing the y group by. Okay. Another thing to remember is that if m equals n, so if these two numbers in the denominators are actually the same number, then what you really have is a circle, right? Because then you're going to be moving the same distance in all four directions, and so you're just going to get a circle out of that, right? If you have a circle, then you can rewrite the equation. Instead of writing this, where you have the same denominator, you can just multiply through by that denominator to get the equation of the circle that we already know and love, right? You don't have to, but usually that's the canonical way of writing it down. So let's practice a little bit. Let's graph some ellipses. This ellipse right here is going to be centered at 0, 0. Okay, m is going to be 2. N is going to be 5. So I plot the center. Then I go 2 units left and right of center. And 5 units above and below center. 2, 3, 4, 5. 1, 2, 3, 4, 5. And there you go. There's the ellipse that we get. Sorry for my poor drawings. But anyway, you get the idea. It's an oval. Right? It's an oval. Okay, so there's the ellipse. Let's do another one. This ellipse would be centered at 3, negative 2. M would be 4. N would be, well, there's no denominator here, but this is the same thing as dividing by 1, right? And the square root of 1 is 1, so N would be 1. So again, I plot the center. Then I go 4 units left and right. 2, 3, 4. 1, 2, 3, 4. And 1 unit up and down. Okay, and there's that ellipse. This is a very long and skinny one. But that's what that ellipse looks like. Okay. So graphing ellipses is really pretty easy, I think. Let's do another one. Oh, this one's just a circle, right? It's a circle. But I included it here just because, you know, a circle is just a special kind of ellipse. A circle is just an ellipse where the two foci coincide, and they're just a single focus or center, right? And you can see that, like if you divide through by 9, right, you get x squared over 9 plus y minus 2 squared over 9 equals 1. And then you can just graph this like you would graph any other ellipse, right? The center is at 0, 2. Then you're going to go 3 units left and right, and 3 units up and down, which is just exactly what we would do if we were graphing it like a circle, right? And you do get a circle, right? You get a circle out of this. Okay, one more. Center here is going to be -1, -2. M is going to be the square root of 7. Square root of 7, let's see, is about 2.6. And n is going to be 3, right? So center at -1, -2. I'm going to go left and right 2.6, 1, 2.6, 1, 2.6. And then I'm going to go up and down 3, 1, 2, 3, 1, 2, 3. This one's going to look almost like a circle because M and N, even though they're not exactly the same, are really close to each other. Okay, so that's that one. Ellipses are no big deal. Let's talk about hyperbola. So hyperbolas are the last type of conic section that we haven't discussed so far. Describing hyperbolas as a set of points in the plane is probably the most difficult of the four. The definition is a little bit difficult to wrap your brain around, so definitely take a look at this graphic, okay? But the definition is as follows, right? A hyperbola is the set of points in a plane whose distances from two fixed points in the plane have a common difference. The two fixed points are called foci, okay? So in other words, if you subtract the distance from one focus from the distance from the other focus, then all of the points that have some fixed difference are going to form what's called a hyperbola. And you should watch this video to get a better sense for what this definition is saying. Okay, so go ahead and pause the video and watch this. Again, a link will be in the Canvas module. What I want to do is walk through the proof of this equation with you. So the equation for a hyperbola with foci 0, -c, and 0, +c is y squared over a squared minus x squared over b squared equals 1, where again 2a is the fixed distance described above, and b squared is c squared minus a squared. The proof is similar, right? Let xy be a point on the hyperbola. The distance from xy to 0, -c would be, so it would be x minus 0 squared plus y minus -c squared. Or in other words, the square root of x squared plus y plus c squared. The distance from xy to 0, +c, maybe I'll call this d1 and d2. This distance is going to be x minus 0 squared plus y minus c squared. So in other words, it's the square root of x squared plus y minus c squared. Now, the absolute value of the difference of these two distances is 2a. Okay? So in other words, the absolute value of d1 minus d2 right, the absolute value of that equals 2a. Okay, by definition. All right. 2a is the fixed distance, we said, right? So 2a. So we can solve this. This is an absolute value equation. Okay, so we know that we can drop the absolute values if we put a plus or minus on the 2a. And then we can solve. So we isolate one of the radicals, square both sides. Isolate a radical, square both sides. Okay. Simplify, regroup. Remember that c squared minus a squared is the same thing as b squared. And then divide through by a squared, b squared. And this is a typo. Actually, we should have y squared over a squared equals... We should have y squared over a squared minus x squared over b squared equals 1. Whoa, okay, I'm off the chart. So sorry, that last step was a typo. It should be y squared over a squared minus x squared over b squared equals 1. Okay? This is what happens when your foci are on the y-axis. If your foci are on the x-axis, then the hyperbola is going to open left and right, and we would have a different equation. Okay. The center of the hyperbola in that derivation was 0, 0, but again, the center could be anywhere. I'm going to come back to this in a second. For graphing purposes, here's what I'm going to say about hyperbolas. So again, instead of using a and b, which means something very specific, I'm going to use m and n. And m is always going to be the thing that we divide the x group by. N is always going to be the thing that we divide the y group by. That's not true of a and b, okay? Which is why I'm changing the letters here. But hyperbolas work like this. So they're going to have center hk, right? H is, again, always the thing that's with your x's. K is always the thing that's with your y's. Okay, it's going to have a center hk. If the x group comes first, then the hyperbola opens left and right. If the y group comes first, then the hyperbola opens up and down. Okay, so that's the difference between these two things. Because this one opens left and right, it's not going to have vertices above and below the center, but it will have vertices left and right of center. And so those are at plus or minus m. Since this one opens up and down, it's the exact opposite case. It's not going to have any vertices left and right of center, but it will have vertices above and below center, right? And they are plus or minus n. Hyperbolas have an asymptotic behavior, which we'll look at when we look at a hyperbola and Desmos here in a second. Okay, but I'm going to tell you how to get these asymptotes without having to memorize these formulas. Okay, you can memorize the formulas if you like, but it's not totally necessary. So let me take you to Desmos here, so we can talk about what a hyperbola looks like. Because a mistake that students often make when they're drawing hyperbolas is that they draw them like a couple of parabolas, and that's not what a hyperbola is. So let me show you in Desmos. No, that's not what I want to do. Here we go. I already had it pulled up over here. Okay, so here's a hyperbola. Okay, the shape of these two things is not parabolic. It looks more like a V than a U, right? A parabola looks kind of like a U, but these things look more like a V. In fact, as you zoom out, you can see that they're practically straight lines, right? There's almost no, like way out here, there's almost no curvature to them at all, right? You don't really notice curvature unless you zoom in really close. Okay. Here are the asymptotes that I was talking about. So you can see that they have this asymptotic behavior. And as you zoom out, yeah, it's like they're practically just makes this x formed by their asymptotes. So that tells you that, in order to graph a hyperbola, we're going to have to graph the asymptotes for sure. They're going to be hugely important. But to show you that the shape, to further convince you that the shape is not a parabola, here is a parabola. Okay, so this is what a parabola looks like. Okay, we can make the parabola wider. Maybe you're just thinking, but the hyperbola, it's just a wide parabola. It's not. Look, I can make this parabola wider. I can multiply by, say, 1/2. It's a little wider, or by 1/4. You see? Or even like 1/8, make it really wide. So now the parabola starts out wider than the hyperbola, but eventually it gets more narrow. And again, as you zoom out, the parabola starts to bend away from the hyperbola, whereas the hyperbola becomes more or less a straight line. So you can see that they're very, very different shapes. They are not the same shape. Again, a parabola is more or less like a U, whereas a hyperbola is kind of like a V. Okay? It's a V, but it does have a rounded vertex. Okay? So you have to be careful there. But just keep that in mind as you go to draw your hyperbolas. Okay? So let's talk about drawing these things. As we saw, the most important thing probably for graphing these is to get the asymptotes right. If you can get the asymptotes right, then you can draw the hyperbola pretty well. So here's how we're going to graph the asymptotes. First, we're going to plot the points m units left and right of center and n units above and below center. Remember, m is what you're dividing your x group by, n is what you're dividing your y group by. And then we'll use the points from step 1 to draw a box. Okay? And then we'll draw the diagonals of the box. The diagonals of that box are the asymptotes. Okay? So let's practice all of this. So part A here is a parabola with center 0, 0. I'm actually going to write down a bunch of information. So the center of this parabola is 0, 0. M is the thing you're dividing your x group by. So in this case, square root of 25, which is 5. N is the square root of the thing you're dividing the y group by. So in this case, square root of 9 is 3. And because your x group leads, this one is going to open left and right. Okay, so it opens left and right. So let's see if we can graph this, okay? So the center is 0, 0. I'm going to start off by graphing this just like it's an ellipse. So I'm going to go 5 units left and right. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 3 units up and down. 1, 2, 3. 1, 2, 3. But then instead of connecting the dots with an ellipse, I'm now going to draw a box. Okay? And then I'm going to draw the diagonals of the box. The diagonals of the box are the asymptotes of the hyperbola. Ooh, that was very messy. Let me try again. Okay, so the diagonals of the box are the asymptotes of the hyperbola. Now this hyperbola opens left and right. So it's going to have, so half of the parabola is going to be here, and the other half is going to be there. Okay, make sure that as you draw this, your hyperbola should get closer and closer to the asymptote. It should never bend away, right? So don't draw this. If you draw it like this, then you're drawing a parabola, and that's wrong, okay? It needs to get closer and closer to the asymptote as you move away from the vertex here. Same thing on the other side. So you're going to have another branch over here, and over here. Okay, so that's what that first hyperbola would look like. None of the dotted stuff is actually part of the hyperbola, right? It's just these two curves. But I draw the dotted stuff to give me some sort of a skeleton to go off of for drawing my hyperbola. Let's do another one. So part B, y squared over 9 minus x squared over 25 equals 1. You'll notice that it's the same thing as part A, only your x and y groups have been switched around. So let's see. This is centered at 0, 0 again. M is still 5. M is always the thing you're dividing your x group by. So M is still 5. N is still 3. But this one opens up and down. This one opens up and down because the y group comes first. So it opens up and down. Okay? So we plot the center, 5 units left and right of center, 3 units above and below center. Don't draw any ellipse, draw a box. Then draw in your asymptotes. They're the diagonal of the box. And now the only difference is that this one opens up and down instead of opening left and right. So instead of having the curve here and here, the curve is going to be here and here. Okay, so that's what that hyperbola looks like. Okay, let's do another one. This one's a little more interesting, I guess. This one is centered at 1, -2. M is 2. N is 6. And this one opens left and right. Okay, so the center is 1, -2. We're going to go 2, 2, 6, 1, 2, 3, 4, 5, 6, and 6. 5, 6. Draw a box. Draw the diagonals of the box. And then draw the hyperbola opening left and right. Okay. One more. I think part D is the same thing as part C, but with the X and Y groups switched around, right? So the center here. Notice though, so the center, the X coordinate of your center is still the number that's with your X group. So it's 1, change the sign though, -2. M is still the number that you're dividing your X group by, so M is 2, N is 6. But this one's going to open, since the Y group comes first, this one is going to open up and down. Okay, so let's draw it. Centered at 1, -2, 1, 2, 1, 2, 6, 6. Draw our box. Draw the diagonals of the box. And then draw the hyperbola opening up and down. Okay, and that's what that hyperbola looks like. Okay, so that's all I have to say about ellipses and hyperbolas. Again, make sure that you're drawing a hyperbola, like a V, not an ellipse, or not a parabola, like a U. Okay, so that's it for 5.2.